Hi everyone, this is about the second part of the radiation. Last time we derived the radiation for the situation where absorption plus stimulated emission plus spontaneous emission and pumping exist in a laser medium. Equation 17 is the radiation for the population inversion delta n, and equation 10 is the radiation for the photon flux phi. We have considered two simple examples. First one is the pumping only, where there is no input photon coming into the medium. In a steady state, from equation 17, d delta n over dt is 0, so we obtained that delta n is, from this equation we obtained that delta n is equal to n minus 2 tau r when there is no external photon or cavity in a medium. Second example is the case where the pumping with external photon flux into the medium, where phi is not 0. Again, from equation 17 we obtained that d delta n over dt is 0 for a steady state condition. So we obtained, as phi is not 0, this term is included, and delta n is equal to n minus 2 tau r over 1 plus 2 tau sigma phi. When phi is 0, we obtain delta n is n minus 2 tau r, so we define this as the population inversion when phi equals 0, so we define that as delta n naught. Then delta n, where phi is not 0, is equal to delta n naught divided by 1 plus phi over phi set. So right, so this is the saturated population inversion when phi is not 0. If phi is 0, then it becomes delta n becomes delta n naught. Where phi set is defined as 1 over 2 tau sigma, and delta n naught is n minus 2 tau r. We'll explain these two situations with graphical interpretation. I considered a case where we have 10 atoms per 1 nanometer cube. Let's consider this cube is 1 nanometer cube, and the pumping ratio R is 1 atoms per nanosecond within this volume, and tau of this atom is assumed to be 3 nanoseconds. So in every 3 nanoseconds, atom decays into the ground state from an excited state, and spontaneous emission happens. So that tau is 3 nanoseconds for this kind of spontaneous emission of this atom. In this case, previously we obtained delta n is equal to n minus 2 tau r. So for this case, n minus 2 tau r is n is 10 and 2 tau r is 6, so we have plus 4. That means n1 is 7 and n2 is 3, so n1 minus n2 is 4. N1 is illustrated with red circle atoms in the ground state with red circles. So we have 7 red circles, the ground state atoms, and the excited state atom is represented with blue circles. So we have 3 excited state atoms and 7 ground state atoms within this volume, where we have 10 atoms per 1 nanometer cube. So we have, in this case, we have delta N0 is plus 4. That's when R is fixed to 1 atoms. Pumping rate is 1 atoms per nanosecond within this volume. And let's consider a case where pumping rate is increased from 1 atoms per nanosecond to 2 atoms per nanosecond. Every other condition is same. Then delta N0 from this equation, delta N0 is n minus 2 tau r. As we increase the pumping rate from 1 atoms per nanometer to 2 atoms per nanosecond, we have more atoms in the excited state, and we obtained delta N0 is equal to minus 2. That's the population inversion is negative. That means we have N1 ground state atom, number of ground state atom is 4, and number of excited state atom is 6. So we have 1, 2, 3, 4, 5, 6 excited state atoms represented with these blue circles, and we have 1, 2, 3, 4 ground state atoms represented with red circles. And if we further increase the pumping rate to 3, then we have delta N not equal to minus 8. That means N1 is 1 and N2 is 9. So we have 9 excited state atoms out of 10 total number of atoms within this cube. And we have 1 ground state atom. By increasing the pumping rate from 1 to 3, we have this situation. So that means the population inversion is increased to minus 8. Right. But if we increase the pumping rate further, we may get more excited state atoms than the total number of atoms. That means if we increase R from 3 atoms per nanosecond to 4 atoms per nanosecond, then we have 2 tau R becomes 16. Sorry. 3 times 4 times 2. 3 times 4 times 2 is 24. So we have 10 minus 24 minus 14. That is more than the total number of atoms. So that does not make sense. So if there exist only 10 atoms within this cube, we cannot make the pumping ratio larger than 3 point something. So pumping rate 4 atoms per nanosecond is not realistic, so we cannot get delta N0 larger than 10, minus 10. So that's the realistic situation. We cannot increase the pumping rate to any number we want. That's not the case. So by increasing are from 1 atoms per nanosecond to 2 to 3 atoms per nanosecond, we can increase the population inversion from +4 to -2 and -8. That's the graphical interpretation about the pumping effect by using this equation. Next, we'll consider the pumping effect, the external photon effect, as well as the pumping effect into a laser medium. Right, pumping effect plus external photon effect into the medium. This situation is exactly same as this case, except for the external photon into the medium. So we have n equal 10 atoms per 1 nanometer cube. R is equal to 3 atoms per nanosecond, and tau is equal to 3 nanoseconds. And we have external photon flux phi, non-zero phi. First, we need to calculate phi set. Phi set is defined as 1/2 tau sigma. So for a given tau and given sigma, we can calculate phi set for a medium, and we increase phi, external photon number, as the integer number of phi set. Right. First we need to calculate phi set, which is 1/2 tau sigma. We consider the sigma, the absorption cross section, is equal to 1/6 times 10 to the minus 20 centimeters squared. That's a typical absorption cross section for a atom. So we put this number, and then for a given tau over 3 nanoseconds, we can calculate phi set is equal to 0.1 photons per nanosecond per nanometer square. That means that is equal to 10 to the 20 10 to the 20 photons per nanosecond per centimeter square. Right. So for a volume of 1 nanometer cube, we'll use this phi set as 0.1 photons per nanosecond per nanometer square. So when phi is equal to phi set, that is a 0.1 photons per nanoseconds per nanometer square, delta n, the population inversion is reduced from delta n naught into delta n naught over 1 plus phi over phi set. As phi is equal to phi set, this becomes 1, so 1 plus 1 becomes 2, so population inversion is decreased by 2. So initial population inversion delta n0 was -8, with this pumping ratio R is equal to 3 atoms per nanosecond. This population inversion is decreased from -8 to -4. That means n1 is equal to 3 and n2 is equal to 7. So I represented this with 3 ground state atoms, n1 is equal to 3, and 7 excited state atoms, n2 is equal to 7. And this one represents the collision of photon and the excited state atom. So we have 2 photons coming out due to the the stimulated emission, and this represents spontaneous emission of photons. Right. Let's consider a next case where external photon number is increased from 0.1 to 0.3 photons per nanoseconds per nanometer square. Then there will be more stimulated emission, and the number of excited state atoms will be decreased, while the number of ground state atoms will be increased. So when, there should be 2, phi is equal to 2 times phi set, so 3 times phi set, then this number becomes 3, and this will be 4. So the population inversion is decreased from -8 to -2. That means number of ground state atom is 4 and number of excited state atom is 6. So as we have more stimulated emission effect inside of this volume, the number of ground state atoms are increased from here 3 to 4, and number of the excited state atom is decreased from 7 to 6. So total delta N becomes -2 per nanometer cube. If we increase, this is a mistake again. If we increase phi to the 7 times phi set, that is 0.7 photons per nanoseconds and nanometer square, delta N becomes delta N naught over 8, that is -1. So we have about N1 about 4.5, N2 5.5. N1 and N2 should be integer because those represent the number of atoms, but this statistically this can happen within 1 nanometer cube. The average number of excited state atom is 5.5, and average number of ground state atom is 4.5 atoms. So these condition represents these three situations represents the case where the number of external photon flux decrease the population inversion within the volume. Those are the graphical interpretation of equation 18. By increasing the photon number of external photon flux, we see that the number of population inversion is decreased with this factor. So we considered here the number of population inversion, and we did not consider this in detail. We just considered the state of atoms with the effect of R pumping rate and the external photon flux phi, and tau and sigma are the properties of the gain medium atoms. So for a given gain medium, we have tau and sigma and the delta N, the total number of atoms per volume. And by varying the external photon flux, we can obtain the population inversion of the medium changes with respect to the external photon number. Those are the graphical representation of those results. And next, this is another review of the results we obtained in the previous PowerPoint file. We obtained the ratio blocked area of photons with respect to the whole area A. So the cross-section and the population inversion are times the A times dz, that's the volume. So this is the population inversion per volume, and A times dz is the volume. So these are these are the area of blocked photons due to the medium divided by the total area. That is equal to d phi over phi. Variation of photons with respect to total input photon, that should be equal to the number of the population inversion within the medium. So with this, from this equation, if we take dz to the left side and phi to the right side, we obtain d phi over dz is equal to minus n. This is delta n times sigma times phi. So from the Beer's law, we also obtained that alpha should be equal to delta n times sigma. So alpha is the gain coefficient and sigma is the cross section, and the delta n is the population inversion we obtain from here, delta n. We can calculate the variation of the absorption by using the number of photon changes or number of the population inversion obtained with this equation. So the gain coefficient gamma with this minus alpha, alpha is absorption coefficient, and if there is a population inversion, delta n is equal to minus, then alpha becomes negative, that means gain is positive. The gain coefficient is with respect to the intensity of light with respect to the distance is defined with this gain coefficient, or in an absorptive medium this should be minus alpha. So when here we obtained alpha is delta n times sigma, and if delta n becomes negative, alpha becomes positive. Negative, that means absorption is negative, that means it's gain. And we obtained gamma, which is the gain coefficient, is equal to minus delta n times sigma. And delta n is given with this delta n naught over 1 plus phi over phi set. We define this as if we define this as the gamma 0, then this is gamma 0 over 1 plus phi over phi set. Here the phi set and delta n naught is defined with the number we already discussed about. So actual gain coefficient gamma decreases with the increased amount of photon flux. That means if we increase photon flux or the power, the intensity, number of photons per centimeter square, or the watt per centimeter square intensity, the absorption coefficient is decreased or saturated by this saturation factor phi set. So as phi set is defined with the the atomic properties of a medium, which is the relaxation time tau and the absorption cross-section sigma per atom, we can find out how will be the absorption change with respect to the photon flux or input intensity to the medium. So this is the consequence of delta n change, saturation of the population inversion due to the external photon number, and the consequence of that is the absorption saturation due to the amount of the input intensity to the medium, light intensity to the medium. And another interesting topic about this gain saturation is the gain narrowing, spectral narrowing, or power broadening. Previously we derived that for a simple damped harmonic oscillator model, we have the relation of refractive index and absorption coefficient by using chi, and the simple chi model can be represented with this equation. And in realistic case, sigma can be represented with the simple approximated result with this one, and the this is the simplified expression for alpha or sigma, because the sigma is the alpha is n times sigma here. Alpha or gamma is delta n times sigma. Alpha is delta n times sigma, and gamma is just minus delta n times sigma. So we have the sigma represented with the harmonic oscillator model equation, chi as a function of omega with this, and this is a approximated expression for this, where capital omega minus small omega square is capital omega plus omega times capital omega minus omega. So capital omega plus omega, where omega is close to capital omega, we approximate that is 2 times small omega. So we have gamma omega here, and we delete omega here and 2 omega term over here. So we have this term approximated result 2 times capital omega minus omega over delta omega. Delta omega is defined as the gamma. So that's the one of the approximated result, and we consider this numerical the numerical values for omega 0 is equal to 3 times 10 to the 8 times 2 pi over 0.5 times 10 to the 6, 10 to the minus 6, that is 0.5 micron wavelength. This is frequency for 0.5 micron wavelength. That is about, you can calculate this. And tau is the lifetime of excited state atom, and G1 is the damping constant 2 times tau 1, and N is the number of atoms per meter cubed, that is 3 times 10 to the 26, and the electric charge, the charge E is equal to 1.6 times 10 to the 19 coulomb, and permittivity of a vacuum is epsilon 0, and m is the mass of electron, and c is the speed of light. Then we have the numerical expression for chi. Imaginary part is like this, and real part is like this, of this expression with all the numbers of the medium, and E epsilon 0 and M and capital N and so on. Then with the expression of chi, we calculate the absorption coefficient alpha. With this non-saturated absorption coefficient alpha. Alpha is delta n times sigma. Delta n is equal, when delta n is equal to delta n naught, that's the case. And in that case, alpha is calculated from this, and the refractive index calculated from this. That's the numerical expression. This is the exact solution for a given expression of chi, given with this. And this is the approximated result. This is the exact solution of sigma omega, the absorption cross-section sigma, as a function of omega, given with the exact the expression of this. This is the approximated result, and the difference between these two becomes this small. So we can replace this expression with this expression. This is the expression I have derived here. This is the exact. This is another approximation, but anyway, this is the expression of without the second approximation. This is the approximated result expression for the second with the second approximation, and that is the difference. This is the original, and this is the second approximated one. So the difference is very small, so we can accept this as a more or less the realistic absorption cross-section as a function of the wavelength. This is the 500 nanometer. Then, as gamma is gamma is delta n times sigma, and delta n is a function of input flux. So delta n is now saturated with the expression we have derived here. But delta n is not delta n 0, but is saturated with delta n not over 1 plus phi over phi set. So that's the expression we have here, delta n not over 1 plus phi over phi set. Then by increasing the number of photon flux, gain is exponential gamma times z. So Right. This is the result without the without the external phi is very small compared to phi set. So that's this is the original expression, and if phi is very small compared to phi set, we have this expression, and compared to the cross section sigma as a function of omega, which is this function, and this is another the representation of this sigma as a function of omega, and as the right, this is the line shade of the imaginary part of chi, and this is G. It is the line shape of sigma is this broad, but the gain curve is much sharper than this. That's because this is gain curve is a function of exponential minus sigma as a function of omega times z. So as this is exponential function of sigma, the intensity of G gain curve is much sharper than the spectral width of sigma or alpha. That's what it is called, the gain narrowing. So this just shows that the gain narrowing without gain saturation. So when the phi is much smaller than phi set, we can see that as the gain or z increases, the gain saturation, the gain narrowing become higher and higher. So this is the when z goes small, so we have a broad spectrum, but as z is increased in this expression, we have higher gain, and the spectral width for this higher gain is much narrower than the original spectral width. That is called the gain narrowing, without considering gain saturation yet, because we consider where phi is much smaller than phi set. Next one is the case where phi set is compatible to phi set. Then due to the phi set saturation of this gain spectrum, we have a broadening of the gain curve compared to the original sigma spectrum of sigma. So as you increase phi more and more from 2.56 times 10 to 25 to the 1.26 times 10 to the 33 photons per millimeter square per second, we have the broadening of the gain curve like this. That is called the power broadening due to the saturation due to this saturation we have this gain saturation, the spectral gain coefficient saturation. Right, so we consider two cases. For a given medium, we have fixed spectral width of the absorption cross-section or absorption coefficient alpha as a function of omega, or sigma as a function of omega. That's right. That's because alpha is delta n times sigma. When delta n is not saturated with the external photon flux, there is a difference between the gain and the absorption coefficient, because gain is related to gamma omega time exponential gamma omega times z. As z increases, the gain curve becomes sharper and sharper as a function of frequency or spectrum. That is called the gain narrowing effect, because absorption coefficient or the cross section of an atom is related to gain curve with this exponential relation. For a given fixed spectral response of a medium gamma omega or sigma omega, the gain curve changes as a function of z, and the spectral width of the gain curve becomes narrower and narrower as z increases. That's what the gain narrowing effect. And another important effect related to the laser medium is saturation broadening. The cross section, or not cross section, for a given spectral cross section sigma, the gain coefficient gamma becomes broader due to the power broadening effect, 1 plus phi over phi z effect. And as the number of photons increased, the gain coefficient becomes narrower and narrower as the due to the input photon flux. That is called the power broadening. The next topic I'd like to explain is the laser cavity, or the photon lifetime due to the laser cavity. Right now we considered about the case where the medium is pumped by external pumping R, and the photon flux into the medium. These equations so far we have described is for the amplification. External photon is amplified by the medium, and the population inversion of the medium is modified due to the external photon flux. That's the activity or mathematical expression to describe optical amplifier. Now we'd like to put this same medium into a cavity. That means the two mirrors on both sides. Then we can make this delays, and for the two mirrors, two external mirrors we need to consider is called the laser cavity. If we put two mirrors in a medium, then we can think about the longitudinal mode or longitudinal mode number n. When n is equal to 1, that means within this cavity there is a one round trip oscillation, complete cycle for one round trip. So there is a knot for each mirror, and we have a standing wave like this, and this is when n is equal to 1. N is equal to 2, then we have a 2 cycles for a round trip. That's when n the longitudinal quantum number is equal to 2 and 3, 4 and 5 and so on. For a given practical cavity length, we have thousands or millions of modes. So n is thousand or billion in general. And there is a transverse mode, which is a quantum number for a cylindrical case. P is a quantum number along the radial direction. L is the quantum number along the theta. So P is equal to 0 and L is equal to 0. That means there is no node along the R direction or the phi direction. There is no node. When P is equal to 1 and L is equal to 0, there is one node along the radial direction and there is no node or zero crossing point along the theta. And if P equals 2, then we have two nodes. Node is the zero crossing point, which is represented by this dark circle. So we have two nodes, and P equals 3, then we have 3 nodes, and so on. L equals 1, let's consider this later. L equals 1, that means we have, along the theta direction, we have one node. So for a complete cycle, we have two nodes. And this is the case where we have two nodes along the 2 cycles along the theta direction and 3 cycles along the theta direction. And for P equal 1, we have one the node zero crossing point along the radial direction, and we have 1 or 2 zero crossing point along the theta direction, and so on. This is a superposition of this with the another of this rotated by 90 degrees. So if we have this one plus 90 degrees rotated along the theta direction, and then we have this mode. This is superposition of this with the another 90 degrees rotated. These are the cylindrical transverse mode. For rectangular shape mirrors, we have the rectangular mode number L and N, and L is the mode number along the x-axis, and the M is the quantum number along the y-axis. So we can think about this as the 1, 0, that is one node along the x-axis, and 2 nodes along the y direction, and so on. We do not consider, we will not derive this one. This is the Maxwell equation satisfying a certain boundary condition. So this is a content will be covered in electrodynamics. So I will not cover this one. Anyway, these are the modes along the transverse and longitudinal direction, and these are the consequence of the laser cavity, 2 mirrors. And this is the important concept we need to consider. This is a photon lifetime in a laser cavity. If there exists a one photon oscillating along the back and forth along the cavity, then there is a lifetime for that photon. That means if we have a real mirror reflectivity, this is R small r, and that is in general 100% reflectivity, that is 1.0, and the scattering loss in a laser cavity is Rs, defined as Rs, and it is normally 0.8 or 0.9, and front mirror reflectivity is 90%, or 50%. It depends on the cavity design, and anyway we define this as RF. Then as if we put 100 photons into the laser cavity, and photon is oscillating back and forth, and whenever it hits the rear mirror there is no loss, but the medium interface we have scattering loss about 80% or 90%. The loss is 10 to the 20%, and whenever it hits the front mirror we have about 10% loss, so the survival rate is 0.9. So whenever it hits the medium or the front mirror, the number of survival photons is decreasing like this, and we can approximate this decreasing ratio as the photon lifetime. And the exponential t over tau photon lifetime, and t is equal to, this is the round trip time, 2L over c is the time for a round trip of photon inside this cavities. In this case is equal to 2L over c is the time, and divided by tau photon lifetime, tau p, is equal to the RF times RS times RF. Small r is 100% reflectivity, RS is about 0.8, so 80% survival rate, and the RF is 90% survival rate. That is approximately, as we take r small r is equal to 1, we have r small s r of small f. So from this relation, this one equals to this, we have the lifetime of photon inside the cavity is equal to 2L over minus C ln Rs RF. So that's so finally we have this representation of photon lifetime with respect to RF and RS. Those are the photon lifetime, and this is the important concept to describe the photon flux intensity inside of cavity. So let's consider radiation with absorption, stimulated emission, spontaneous emission, pumping plus cavity loss. Cavity loss is included by using this photon lifetime, and the rest of the equation are all the same, 17, and equation 19 is modified to the 20. d phi over dt is equal to minus c sigma phi times delta n, and this is the extra term minus phi over tau p. It is similar to the relaxation of the excited state atom with this n over tau. This is actually n2 over tau, and similarly we have photon relaxation rate, it is minus phi over tau p. Then by using these two equations we can consider before threshold phi equals 0, then we have from equation 17 phi is equal to 0, so we ignore this one, and from this is equal to 0, and we have relation for delta L. Delta L is n minus 2 tau r. It is same as the previous equation because equation 17 is not modified at all. And after threshold, when that phi is not 0, then it is modified, so we get a different result. And delta from from equation 20, which is equal to 0 for steady state, we obtain delta n is equal to minus 1 over c tau p over times sigma. And as delta n is given, we put into equation 17, then we have phi, relation of phi. So if we have delta n put into this, and we have phi here. So we have this relation, and phi is equal to 1 over 2 tau sigma minus this expression. From equation 20 to, if we put the equation 20 to 23 by replacing delta n, we have phi is equal to like this, c times tau p r minus 1 over 2 tau times 1 over sigma plus n c tau p. And if we take c tau p on the left side, we have times r minus this value, and we define threshold pumping rate as 1 over 2 tau n plus 1 over c tau p sigma. Then we have a simple relation like this, because this is a constant for a given cavity lifetime tau p. We have this. So if we plot this delta n if phi is equal to 0, delta n is n minus 2 tau r. So if we plot delta n as a function of r, this is a linear function. And if when phi is not equal to 0, non-zero, then delta n is constant. So these are the two cases. When phi is equal to 0, we have linear relation of delta n with respect to r. And we have flat relation of delta n as a function of r, given like this and given like this. These are two equations, 21 and 22. So this is equation 21 and this is equation 22. So there is a threshold where phi is equal to 0 and is keep increasing by increasing the pumping rate. And when there exists a non-zero photon inside the cavity, even though we increase the pumping rate, the population inversion does not change. That's what it is. If we plot phi into two regions where phi is equal to 0, that means phi should be 0, constant. And as phi is not 0, then phi becomes like this. So as a function of r, phi is c times tau p r minus r threshold. So we have this linear relation of phi as a function of r. And starting point where phi is not become 0 is the threshold pumping rate. It is a constant for a given cavity, and this number, threshold pumping rate, is an important characteristic of a cavity defined by tau p. So these two are the important characteristic of a laser as a function of the pumping rate, delta n as a function of pumping rate, and phi as a function of pumping rate. These are examples you can find in literature. Laser diode, forward current. Laser diode pumping is defined by the forward current. So this is R pumping rate. And output power is like this. It depends on temperature. This is a specific curve for a specific laser diode. At 25 degrees we have this threshold current like here, and we have this ratio, and as temperature becomes higher, threshold current becomes much larger, and the slope is a little bit decreased here. And that's the reason why temperature control is very important for diode lasers. And for high accuracy, for a sensitive measurement or sensitive device, temperature control is essential, because this the laser characteristic curve, which is defined like this, is very sensitive to the temperature. And this is another the output power versus the pumping rate curve for a fiber laser. This parameter change is the length of the fiber. By changing the length of fiber from 8 to 28 meters, from the black to the purple curve, threshold changes and the slope changes as well. This is the slope, and this is threshold. And this curve is the characteristic curve for a given laser. So whenever you like to buy a laser, you should find out how is the power versus pumping rate. It is defined by the pumping current, forward current, versus the power of the laser for a diode laser. This is the input pump laser. For a fiber laser is pumped by another diode laser. So this is the pump power, that means power of the diode laser, and this is the fiber laser output. So we have this characteristic curve, which is explained here. So the mathematical expression of this threshold and the efficiency curve, C times tau p times R. This is the slope. C times tau p is the slope, and that's the important parameter which determines the efficiency of a laser, and the threshold as well. And those slope and threshold is modeled by the parameters we define here: tau p, sigma, and number of atoms, and lifetime of excited state atom, and so on. But this is about the second part of ray diffusion, and these curves are important, and you need to understand these curves. That's about it.